Good morning.
Morning.
Six people so far. I guess I'll wait for a few more to arrive. It's always nice to turn on the camera when you zoom in so I can see you. Okay, let's get started. So let me share my screen. So today I spoke about this very recent paper on neural encoding and the scaling law of neural population responses. I think it's a very fundamental paper, a very important paper. But of course, it's a bit mathematical. So I guess the derivation of this theory is not really the prime goal of this class, but I think it's always rewarding to try to really follow the derivations. That's why I spent a great effort to lay it down, and hopefully you were able to follow. Really, the basics is the computation of eigenvalues. It's really about the spectrum, about eigenvalues. So I think if you are not very familiar with eigenvalues, then I would really recommend you take the additional time to look up how they're defined and how you can use them. Oh, hi, at face. That's nice. Hi, Marco. Thanks for throwing the camera. Nice of you.
Sorry for being late.
No worries. So let's go through this. I had two parts. One is just presenting the paper, and the other one was presenting the mathematical supplement of the paper. So let's go to the questions, maybe. Let's start from the questions, unless I'll also try to open the chat. Let's open the chat. Oops, now it disappeared. Yeah, the chat. So how can we estimate the unbiased signal variance of population responses irrespective of noise? Right, you have, in this paper, they showed visual stimuli to neurons in primary visual cortex. They measured the responses, but they want not the response variance, but the signal variance. They compose the response into signal plus noise, and they want to estimate the signal variance without being affected by the noise. What is the trick? What do they do? What did they do?
They made several repetitions, and since the noise is, if you average it over several repetitions, then the noise cancels out.
Yeah, exactly. They assume they present the same stimuli more than once. And so they write the response is the signal plus the noise. And the noise term, they assume has mean zero and is independent across repetitions, yeah. And then they can write the signal variance. They can estimate it with the formula in here. Yeah, they can estimate the signal variance from the covariance of the responses, which is outlined in the second. How do I switch? Here. So the covariance here of F is the signal variance, because the terms because the noise is IID, cross repeats. Good. That's more questions. How many dimensions at most has the manifold of neural population response to n stimuli?
I would say n.
Yes, yeah, that's simply follows from this fact that the eigenvalues, right, of linear transformation is given by the transformation transpose times the transformation, and that's the same as this. So either you have here this is a matrix n stimuli squared, and here's a matrix n neurons squared, and the spectrum, you cannot have more eigenvalues than you have rows and columns in your matrix, so cannot be more than n. This is basically an algebra. So do classical neural response models provide a good account of the dimensionality of the neural response manifold? So they used this, they presented these stimuli, and they computed here the simple neural response model, which is kind of very simple to this linear receptive fields that we estimated, that we showed how to estimate last week. They had a little trick here. They made it low rank. They made a low rank estimate, but it's essentially the same thing as we have seen in class. So to these models here, this is simply the kind of reverse correlation, linear receptive field model, and this is an idealization in terms of a Gabor model where you assume you zero, the signal is zero outside. Here, see, look at the noise, you get noise outside. Do either one of these, or especially this Gabor model, provide a good account for the dimensionality of population responses?
I think I thought there was a big difference between the variance, the cumulative variance predicted by the RF model and what we actually see.
Sorry, I could not hear you very well. I have a...
Oh, sorry. There is quite a difference between the RF model prediction, yes,
Yeah,
in this slide, and what we see.
Yeah, here, so it shows that you need many fewer principal components to account for the variance of the RF model, but the neural data actually, the spectrum or the cumulative variance increases more slowly. So there's something that is missing, right, with the classical receptive field model, and it's quite large. There's like a factor of 10 here, so it looks like closer than it is. So yeah, there's something is missing with these models, and that's why this motivates that these authors did not want to look at these models. They felt they were inadequate, but just try to look at the manifold itself, right? What is the manifold of this response, population response? So what scaling law describes the decay of the neural response spectrum as a function of principal component number? So this is also here, right? Oops. Here, this is the scaling law. They noted that for many different animals, every line here is a different animal. These curves, they are very similar. So there's something presumably universal about this here. And the scaling law is what is here? It's the slope here. This is a log-log plot. So the slope here is the exponent. So for the exponent, they find here, right, this border of fractality, which is given by 1 + 2 over d, where d is the dimensionality of the stimulus ensemble. So does the spectrum decay faster or slower than the border of fractality? Is this a law that they describe, is this an upper bound or a lower bound?
Looking from data, I would say a lower bound, or all of the data we have are slightly above the border of fractality.
Yeah, okay. In terms of the exponent, right? In terms of the exponent, it's a lower bound, yeah. But in terms of the spectrum, it is.
It's an upper bound.
Yeah, it's an upper bound. The spectrum must decay faster than this. It cannot decay. If it decays, the argument that is what happens if it would decay slower than this? What does the theory say? Right? What if you had a neural ensemble and you computed the principal components and it would decay like this? It would just cross this line here. have a tail like this. What would it mean for the manifold of neural responses? It would not be continuous and differentiable, which means if you were to change the stimulus a tiny amount, then the neural response would change by a large amount. And the assumption is that is not what brains do. This would hinder brains of being able to decode the neural activity. If a slight change in the outside world gets mapped onto a very different state in the neural population, then it would be very hard to decode this ensemble and be able to reach decisions and have a motor plans that are well adjusted to the sensory inputs. Kind of there's something intrinsically, right? Intrinsically, the neural code in the brain must be continuous with respect to the outside world. Do you have any questions about this paper? They have a figure somewhere in the paper about a manifold that is not continuous, where the spectrum decays more slowly. They have, let's see, where are they? Find this figure somewhere. Should be in my. No, it's not here. I think I don't have the paper here in my folder. Sorry, but there's a figure somewhere in the paper you can look up. This is just a supplement, yeah. Good. Then let's go to the other part of the lecture here, where I derived the math, starting with the Minkowski dimension, right? So the idea is really the dimensionality is how many spheres you must place around your curve of interest, so you completely cover it, and to measure then the length of the curve. So really, how many spheres do you need as a function of the diameter, as the diameter goes to 0? And so the scaling law is then in the log-log plot, the number of spheres versus the diameter, and that gives you the dimension. And that's all you need. So you need to characterize the dimensionality of the code like this. And let's see, what other questions did I have? My questions are here. Why does CVPCA, cross-validated PCA, achieve an unbiased estimate of signal variance? Okay, that's the same question that we already had, more or less. Right, this is because of this here. We had it in the. It's because the noise is assumed to be independent across repeats, which means if you compute the cross correlation here, or the expectation of these two, then you have the cross terms V1, V2 here, and those drop out because they're assumed to be uncorrelated. And the V1 squared and V2 squared terms do not appear. So you just get the signal variance. Good. The other question was, what is the Minkowski dimension of the two-dimensional plane?
Sorry, but here we mean the whole two-dimensional plane or a figure inside the plane?
It's the same. Just a piece of paper, a two-dimensional piece of paper.
Okay, okay.
I mean, in practice, we always mean the dimension of a finite manifold. I mean, you know the answer, right? A two-dimensional plane, you know what is the dimensionality. Now we just
It's 2.
it's
right?
2, obviously, but it also agrees with the Minkowski dimension. The same way as you can convince yourself that if you make a strained light and you make these spheres, then it doesn't matter how small you make them. You just need L equals n delta times delta line. So you need n spheres. Each of one gives you a distance delta, and then you need n delta times delta times of such spheres to measure the length of the line, right? So where n delta.
And delta,
Hmm?
no, and delta will be 1 over delta, or delta to the minus 1.
Yeah, n delta
So,
would
yeah.
be 1 over delta. Yeah. And the same thing you can convince yourself if you arrange the spheres on the plane, right? You make them like this. You can easily convince yourself that you're going to need here 1 over minus 2. We need delta squared. 1 over delta squared n spheres. Just draw it out, and it's just nice to convince yourself by going through the same argument here for 2D that you get the answer you'd expect. Which assumptions are the weakest in the derivation of the scaling law? There are actually not so many assumptions.
Maybe noise independence.
Pardon?
Maybe noise independence.
Maybe one assumption, maybe that is that the noise is, that the signal is fixed, right? And the noise is, independent across repeats. I mean, when you look at their plot here, this is, they presented a stimulus stimuli many times. Here, I think 60, I don't know, there's some number of stimuli here shown. And this is from the first half of the data and from the second half of the presentation. And you can see the stimuli, the responses are identical. You can see here and here, but they're not exactly identical. Here, these two bins are equally red, and here this one is not as red. So, I mean, they're nicely agreeing, but they're not perfectly identical, right? So clearly there is something that remains variable. It could be that the brain is constantly learning and constantly adapting to stimuli, and so the signal could be changing as a function, you know, of the order of the history. So this is clearly one thing where this model does not take into account that the brain might be plastic. Here's another thing I find, this here, that the signal has, that the noise has mean 0. Not sure. It would be nice to calculate the noise from these two repeats and see really how close to 0 it is. I think the authors didn't show how close to 0 it is.
But if we take the empirical mean as signal, then I think we kind of want to assume that the noise is 0, and then we put overrest in the signal, right?
Yeah, we are forcing it, right, into being 0, but with 2 repeats, you cannot do much more than that. But maybe with 4 repeats, one could really see, one could add many estimates of the signal and get, and also many estimates of the noise and see whether it really has mean 0. Yeah, these are not many assumptions. I think that's why this is a kind of a good theory. Then what questions did I have? Can we apply the same method to estimate the neural spectrum of the premotor code of a complex behavior? Right, so we are dealing here with this primary visual cortex, which is a sensory brain area. So the question is, could you use this method to measure, for example, the neural encoding of a motor behavior? For example, the song of a songbird or so. Could you go into could you do neural recordings from 1,000 or 10,000 neurons in the premotor brain area that controls the complex behavior, and could you apply the same method?
I would assume it doesn't really change whether it's sensory or motor, so we can still do it.
Yeah, I'm not sure.
Maybe it's difficult to have the bird repeat the same procedure exactly twice, in the same way.
Yeah, I would say it's impossible. Yeah, the bird would sing every time a different song. There's no such concept as a repetition of a behavior. It's always some variability you cannot control. So I would say this method would not work for motor areas. I mean, that's why one of the projects in this class that we'll learn more about end of May is about just estimating the continuity of a motor code. So for the motor areas, it also makes sense that the code is continuous, right? That small changes in overall population activity give rise to only small changes in vocal output. But we can't use this separation of signal and noise, unfortunately. That's why we need a different method to estimate the continuity of a premotor code. Which means this is kind of research. This is, I would say, an interesting topic for research these days in neuroscience research. Okay, so these are all the questions I had. Do you have any more questions about this?
Just one question about this. Assuming we are doing this experiment not with the birds but with humans,
Yeah.
if we ask the person to repeat a certain movement, don't we actually achieve the same result?
But you cannot achieve the same movement.
Ah, I see. Like the same exact movement.
Yeah, nobody can achieve the exact same movement, so it's impossible.
Ah, okay, I understand.
Yeah. Because here the details really matter, right? We have a theory that deals with the decay of the spectrum of any order, right? So everything matters till the very end. So that's why to really use the theory, we need a perfect repetition of the motor signal in the brain, which is not possible. Okay, so yeah, congratulations. You have now, see in the chat, is there something in the chat? Oh yeah, there's something in the chat. Let's see. Why is ES on page 4 at the bottom left? Page 4, but page 4 is this? No. Some other page 4? This? No. Where is ES? Is it here? So this here at the bottom right? See, where is it? Why is ES mu S squared? This here, mu S squared. Oh, this. Why is this smaller than some lambda I at the bottom left? Okay, good. Because I'm dealing here with the largest. I have ordered the eigenvalues such that the first one is the largest, the second one is the second largest, and so on. And here I take n, the n largest eigenvalues, which means that any projection here, this is a projection onto n vectors, right? I pick n vectors. Any projection onto n vectors must account for less variance than the n largest eigenvalues. Does that, yeah, does it make sense? It just, I haven't told you which ones, which I said pick n vectors, and I didn't say exactly. So at the worst case, you pick the n vectors associated with the n largest eigenvalues, but then it's just equal, and otherwise it's small. Okay, any more questions? Okay, yeah, I hope the mathematicians among you enjoyed this and feel encouraged to come up with more fundamental laws of encoding in the brain. So there's still, given that this paper was just published, I don't know, 2 years ago or so, it's much to be discovered, much important work to be done. Okay, so I think we're gonna close here, give you a little break, and then you go to the project sessions. Okay, so have a nice week.
Good week.
Yeah, bye everyone.
Bye.
Thank you. Bye.
Thank you. You too. Bye.
Thank you.